So we're now recording. Everyone, welcome to the fifth workshop of this series on forward kinematics. This was created by Sam Triest, a UR alumni, and myself, Bennett Hedegaard, over the summer. So this workshop, we're going to recap what has gone on in the last four workshops, cover some basics of robotic algorithms, discuss a bit what goes into designing a simulator. This is something that we already did, of course, for the workshops. Like we made it up, but thinking about the process of why we made the decisions we did could be valuable. Then, of course, we'll cover forward kinematics for robot arms. What does that mean? What does that look like for the arm we're building this semester in particular? And then we'll just mention some resources near the end about these topics and where else you can learn about these things at UR. So to recap, where are we in the workshop series? We've learned the fundamentals of CAD. We've then used those skills in Fusion 360 to design the parts of the arm. In workshop 3, we learned, how could we print the arm itself? Workshop 3.5, we haven't mentioned a lot, but had we been in person, we have a set of instructions and the materials needed to build the arm. So that's all documented out. And this last workshop, we learned how to control the arm using Python. Obviously, this semester, all the servos are virtual, but in the future, stepper motors, would work in person. As for what this actually gives us in terms of functionality, the arm is assembled. We can control it via joint angles, as we did in the exercises for the last workshop. We can also control it using teleoperation. You could plug in a USB controller and map a joystick to moving the servo back and forth. We didn't demonstrate it because sharing a video of that would not be very exciting. But the code we've written and the code you've sort of worked on in workshop 4, we have the capability. We've done it in the past. What do we want to do next? We want to be able to control the arm by telling it some XY position. Right now we can't tell the end of the arm to move to a certain place, so it's not very useful. And we also can't do anything autonomous yet. Maybe even more ambitious than having it go somewhere that we tell it is give it an XY point and have it figure out how to get there. And we'll do that next workshop. So to start, what does an intelligent system actually need? In order to make the arm move intelligently, we need to incorporate some sort of control system into the arm. And such that the system sort of requires the robot to be able to do a few things. We want to be able to form goals. We want to make observations of the state or the environment of either the state of the robot or the environment around the robot. And then the robot needs to be able to take actions that affect the state or its own state in some way. And this idea of a being or a robot as an agent is just also another term for it. So let's kind of define some of those terms. Really just an agent is something that deliberately acts. It's commonly used in AI just as a general term for the thing which is making decisions. The environment is sort of the general dynamic system within which the agent operates, and it typically has some unknown internal state. If you think about the world around the arm doesn't know a lot of things apart from its joint angles really. But even more complex systems like a mobile robot, it might not know every single detail of the world. And so instead it needs to form some sort of state of its own. So the state is how the robot characterizes the environment. And it kind of hopes to represent everything we care about in the future or everything we care about that can impact the future. And so I think it's an important note, the difference between what the robot's representation is, and that's not going to be everything in the world. And the decisions that we put in there, are pretty important. This paradigm is often called sense, plan, act, where we sense at some time t by using sensors to collect information about the robots and the environment. We're going to form some representation of what we just saw, call it state x. We'll pass it into some planner and use that state information to decide how to achieve whatever our current goal is. Maybe we generate some action and we throw that out into the world or the environment. And this entity is the issue here. We don't have control over the environment. So in noisy systems, maybe we can't exactly tell where we are within the world, or we can't tell how the world will respond to our actions. If these two lines connected to each other, robotics would be very easy. And almost the entirety of robotics research goes into the fact that these arrows are not connected. And finally, once we've acted out into the world, we get back some observation. We're at the next time step, and we can iterate on that idea. That's the first section. Are there any questions so far? Give it like 5 seconds. So how do we formalize the arm within the system? First, what are the goals that we want the arm to be able to do? Maybe get the end effector to a certain position in XY space in this figure. Maybe it's the green X, and we've kind of shown the arm, as these links. The state of the arm is its joint angles. Let's say they're theta1 and theta2. Obviously, we can control these currently, but we can't control the end effector. And really, the only thing we can control are these actions of changing the joint angles, maybe varying these in some way. In the notes, something which we suggest people think over, obviously answering live maybe doesn't work as well. But think through this, like, what can we currently sense? How do we currently act? And how are we planning? Which of these things is difficult in the system? For one, I guess sensing, we can directly observe the state. We know the joint angles, we're directly setting them, but this isn't always as easy in other problems. Robots with LiDAR and big point clouds coming in, cameras with very high dimensional images. Robots often do not know many things about the world, and sensing is a big issue in general. For acting, the arm is also fairly simple. We can directly change the state, so we can set the angles to whatever we want. We could be like, the one issue with the current arm design that we have is you could set the angles to dangerous configurations where the links of the arm will collide with each other, and we have no way to control that currently, but that's the power of having freedom, I guess. And finally, like, acting is not, again, always as easy with drones, autonomous vehicles. There's not always like a one-to-one mapping between what you tell it to do and what it does, but also maybe like the control set is more limited in some way. Like if you're in a submarine, if you're on the mate team, you're going to have some difficulty precisely defining, I guess, what the current action is in some deterministic way. I'm planning, this is the hard part. This is why this and next workshop mentioned planning so much. So why is planning so hard for the arm? If you think about it, we're giving the robot goals as XY coordinates within the 2D plane. So if we knew where the end effector was, we could easily tell, have we reached the goal or not based on how close we are, maybe. So this mapping is fairly easy. If it's a little distance, great, we've won. But we only have direct observation of the joint angles. We don't actually have any idea of where the end effector is. And so the robot has no idea whether or not it's currently reaching its goal. So this mapping is the issue here. We can formalize this a bit more clearly by saying the concern is that the goal and the state are in different spaces. The joint angles here, which are our state, they're in some joint space. And then the goal point is in some operational space. And this is typically just a term for the space within which the robot acts, often, just the real world. But we can't plan unless we either move the goals over to the joint space or we move the state over to the operational space. And these two problems actually have names. One of them is the name of the workshop. Moving goals to joint space is typically called inverse kinematics. And this is hard for arms. So first off, what does moving goals to joint space mean? Think about, like, if I want to put my hand right here in space, and you'll notice I'm able to try to hold it still. Like, I can move my arm many ways and get my hand to the same point. That's, kind of the nature of having more degrees of freedom than are needed to get to a certain location with an arm. And this is why it's difficult. One end effector pose can have many solutions, especially as you're adding more joints or more degrees of freedom, and thus increasing the dimension of the joint space. So it's both a problem because you have more options, but as you try to search over spaces with more dimensions, it just tends to be more and more options exponentially faster, and you turn out with slow algorithms. Second option is moving the states to the operational space, and this is forward kinematics. And this is generally easier because we have some state, and the end effector pose will be a deterministic function of that state. So for a given set of joint angles, we can exactly compute where will the end of the arm end up. And this will be the goal of what we're doing today. And this finally gives us a mapping of an F of theta1 and theta2, and we could turn that into end effector and then detect, are we at the goal? So finally, the graphic is connected together. So forward kinematics is going to be what we're discussing here. But forward kinematics is highly dependent on the particular design of a robot. Here we're focusing on forward kinematics for 2D arms, but this will be completely different for mobile robots or soft robots, 3D manipulators. We've put in here Lavelle chapter 3. This planning algorithms textbook is a widely cited source in the field. Chapter 3 covers a lot of kinematic stuff. A lot of it's kind of boring math. But section 3.3 covers kind of what we're discussing in this workshop, as well as 3D extensions. So that's a great resource, if you're actually trying to implement these things for a project sometime. So what's the formal mechanism that we're using? It's going to be a link. We're going to define a link. You can kind of notice the shape of one of those arm segments as a translation from some origin to some endpoint. Each of these links will be located, or each of these rather points will be located at some point xy and an orientation theta. The tuple of xy theta is often called a pose because you care about both where you are and where the arm's facing. You can kind of think of theta as the default orientation of the link. Off of that, we're going to have some distance d. That's the length between the link origin and the endpoint. And finally, we can actuate the link as well. So from the theta pose, we're able to actuate some other angle phi. And this is the controlled disjoint angle that we're actually controlling in our code. Now, using this, we can kind of compute the position and orientation of a link's endpoint from its origin. And we can view one link as a sort of a transformation between one frame and the frame of the next link. More precisely, we had some location and initial angle within the global frame, and we're going to end up with some other position and global angle. More precisely, the second of these angles will be equal to the first plus whatever the angular offset was, and then we just go some distance along that, and what do you know, we're at the new position. And you can maybe see how this could be somewhat trigonometry related. The translation is going to be a function of this angle, and we're displacing by some radius. So one could imagine there's going to be a particular solution for that. It's the radius times the cosine of what the angle was. Similar thing, sine corresponds to y, and this gives us the exact thing we want. This gives us how to compute this angle. It's just the sum of these two because this line is parallel to the offset from the link, and then we have our x and y offsets to find the next link's position. So what do we do next? We can just apply this over and over using each link's length and phi offset angle. And kinematic chains are really that simple. You apply some easy to define transformation to each link in the chain. And as long as you define them all in the same way, you can just verbatim apply it over and over. I have here a Desmos demonstration of this idea. Really, it's just a fancier way to draw what the workshop will end up implementing. But of particular note is the fact that this is just a graphing calculator. This is entirely deterministic mapping between whatever numbers you give it, and can draw functions in that space. And so can post the link in the chat as an aside, kind of. But in just a second, I'll show why is this something that's worth reading. That's the link. So of particular note, a few things. First off, we can control each of these links independently. Just kind of, that's how joint angles work. But they're all using the same math on the inside. So link one is applying, we add on this link length plus the result of the last angle. We offset by that amount, and we add it on to what the x was before. And the exact same format applies, for all of these links. And the end effector is just some point at the end. But we could easily add, copy pasting, any number of links more. And that's kind of the other part of a kinematic chain, is that a chain can have many links. As long as you define things in a general way, you can apply the same math over and over. So there's an important maybe step, what just enabled what we saw. And there are sort of two realizations that are important. One is that link origins depend only on earlier links. So the location of link one will affect link two, but the location of link two has no bearing on the location of link one. And then the endpoint of one link is the origin of the next. This is kind of a subtle point that we deliberately defined it that way. This entire mathematical model is built from scratch, so we could have done anything. You'll notice in this graphic, I put the endpoint as the end of the arm, but if there was another link, maybe a circle would be here, we'd want the endpoint to be at the center of that circle, so that within, let's say this link is link I, we want the origin of link I+1 to be at the exact endpoint of the end of this link, so that we can have clear translation between the two. This would be in the center of link I rather than the end of it. And that's just a subtle point that's worth considering when you're measuring out these systems from CAD models. And so if we know, where the first link ends, we can precisely, just copy paste. That's where link 2 starts. Now here we've just kind of fixed the position of the arm in the simulator, which we'll be working with as we code during this workshop. And we could really just set this to whatever. You can assume it's 0, 0, 0 if you want. In this case, we've defined it as, I think, 0, 5 is the origin, and then it starts at angle, I guess, pi over 2, kind of arbitrary. And then finally, you can just compute the position of each link, yeah, given the previous one. Like that's the process we've just described. It works. So we have this fixed point. We offset by some angle. We use theta1. We now have this new endpoint. It becomes the origin of link 2. We offset by an angle. We go some distance, and we're there. There we go. The end effector's orientation, obviously in 2D doesn't make much sense. But if you think about in a 3D, like it really matters which way my hand's facing if I'm trying to pick something up. So getting used to the formalism of pose and orientation is useful in 2D before we go to 3D. So yeah, that's really it. It is pretty simple. Some resources are these as follows. Probabilistic Robotics is one textbook. It's an introduction to a lot of probabilistic algorithms. So dealing with uncertainty, dealing with like noisy sensing for robot control. And it focuses on mobile robots. So you're going to map the environment. You'll want to localize within it. And the problem of doing this both at the same time or simultaneously is SLAM, simultaneous localization and mapping. So that's a bit more, applied. Like you could write this for a mobile robot, and maybe some project in the club is trying to do so. As for planned algorithms, we already mentioned this. It's more of an introduction to a lot of different concepts. It has a lot of the stuff this workshop and the next workshop touch on, just more in depth and way more mathematical notation. But it is also just a great resource for finding out, how do I start with maybe the 3D version of this problem, for example. Finally, what are the courses at the school that touch on these things? EC 213 and 232 are both taught by Professor Thomas Howard. EC 231 is robot control. Its focus is on arms and mathematical fundamentals. It's being taught next spring, I think. And then 232 is mobile robots. This focuses on wheeled robots and the implementation of more algorithms in ROS. So it's, I guess, more code practice in the end than 231 based on how Sam described it. And that's going to be taught not this spring, but next. These two alternate each spring, I think. So yeah, there's all that. Kind of as a final footnote, what was the thought process that goes into simulation? Why would we use simulation rather than just building the arm from scratch and testing things there? So simulation is used very widely in robotics, and there are some obvious reasons why it is useful. Physical robots are breakable. If you make a mistake in the algorithm, you could just damage your robot. That's not a great thing for testing. They're also, of course, expensive. It's like $25,000 or something obscene for, it's like a real lab. Baxter, yeah. Baxter is one of the robots in the lab we have on campus. You don't want to break that. So let's try to use simulation for that reason. There's also the idea of generality. As you'll see in the workshop code today, we can simulate an arm with any number of degrees of freedom. Why you'd want to do so, maybe isn't as useful until you have a physical platform. But for testing algorithms, for prototyping, for finding out, what arm would I need if I wanted to cover a certain area of space? That's a very abstract question, and without having some sort of simulation to compute, what is the reachable configuration space of the robot, we kind of be without luck. So we can test general systems by writing general simulations. And yeah, it's just easier to change things as well, flexibility. Finally, physical robots are actually slow. So if you're doing, wide testing, I'll get to a question in the chat in just a sec. If you're doing multi-iteration testing, you probably want the ability to do 1,000 trials in the time it would take a physical robot to do one. So that's useful. In terms of taking EC 231 and 232, 231 and 232 are both as far as I can tell, as a CS major, they seem like the highest, maybe the highest level EC classes I know of, as in they have everything as prerequisites. That said, I took EC 232 last semester as a sophomore in my sophomore spring. It was not at all easy, but I came from a unique background of having taken the AI course in computer science. And so I kind of knew what I was getting into a bit. But like from my experience, I guess, taking 232 is typically, junior or senior spring. And if you're going to take both, it'll be one's junior year, one's senior year. But if you're like a sophomore who's taken AI and really wants to learn either of these topics, in your sophomore spring rather than junior, that's the advice there.
Bennett, I don't know
Yeah.
if you mentioned, but are those classes for like everyone, or they just you have to be within the major, or is it like are those intro courses? I didn't hear.
So yeah, as far as I can, at least in EC and computer science, most like upper level courses don't actually enforce strict prerequisites. Obviously, there are many things that are suggested. Specifically, like 232 wanted circuits and C and some other stuff in EC that I didn't do. The point is I didn't have any EC prerequisites for 232, and AI got me through. I'm not saying that's recommended. You could read, the course catalog for specifics, but Professor Howard is fairly flexible, and if you're willing to put in the work, or you're just coming in with the right experience, a lot of these things maybe don't need all of the EC classes.
Okay, yeah, that makes sense.
Sorry,
Oh,
slightly unrelated. Does it kind of go the same way for CS classes too? Like as an ECE major, could I take stuff in the CS department?
I mean, I haven't tried to do as much because, I just took the classes before as a CS major, but most, like, at least for the upper level classes that I've cared about, most of the professors have been A, like pretty chill about their topic, and B, like just interested in showing it to people. So if you ever have specific questions, I would recommend just emailing professors and asking. Most of them will say like, we recommend it, but secretly you don't have to. And like, I'm not going to say that any of these things are ever easy, but I think prerequisites are often just to make sure the major is done in like intelligent order, because like taking 232 before the rest of your EC stuff makes no sense. But if you're just going to take one EC course, I think it made some sense for me. And so, I would suggest emailing. Emailing tends to not hurt. Yeah.
All right. Thank you.
Absolutely. Yeah. Like, we have all the time in the world. So that's why we want simulation. What did it take to make this particular simulation? Kind of a core idea is the right level of detail. We want to ignore some things of the robot or of the world, and we want to include other things in a simulation. So for our case here, and this is both for this workshop and next, we want to get the arm's end effector to a certain XY coordinate. So we've included, the position of the goal point, the position of the arm's end effector. This includes the joint angles and the link lengths of the arm so that we can compute that. And then we want to be able to tell, like, are the joint angles putting the end effector on the goal point? These two, of course, we basically kind of covered in this workshop. And finding and going towards the goal will be the goal of next workshop. So that's our simulation. Let's actually look at it. I think that would be worthwhile. So this is going to be what you see if you try to run the workshop code. I'll do it in just a second, but we have the 2D joint space here where we have theta1. It's going to go from 0 to 2 pi, and theta2 from 0 to 2 pi as well. And you can see here, nothing's happening. And let's look at why that is. So first off, I'm inside of the workshop folder and then the Ford Kinematics folder for this workshop in particular. To run the workshop's code, I'm going to do Python 3 GUI.py. We'll bring up the GUI and call the other stuff we need. And here's what we see. As I mentioned, you can move around in the joint space, and it's changing the arm over here, but it's not doing anything because the code is not yet implemented. That's the workshop's exercise. So this is the folder or the file that we care about. We are in arm.py inside of the Ford Kinematics folder, for this workshop. There's a bunch of details, like the arm is going to be a series of links. Some of them are controllable, and you get passed in a link list, and you'll build that accordingly. And this is going to be the function that we're working with. So it's called get joint poses. It's going to use the current joint angles to return the poses of all the links in the arm. And this will be implemented, as a part of this workshop. Great, glad I left that comment for myself. The output of this function is a NumPy array of dimension n+1 by 3. So it's n+1 rows and 3 columns. You don't really need to worry about what this file type is. It's just, or data type, it's just useful. So it's going to be an array of those dimensions. Each row is going to be the pose x, y, theta of the origin of the nth length of the arm. and the n+1th row is the pose of the end effector. So how are we going to compute that? We start with just a array of 3 zeros. So that's really what this is. We're creating an array of 3 zeros, and we're putting it inside of a list. Like, kind of two things are happening here. So we have that, and yeah, we store it in a list, as I've said in the comment. Then we're going to loop over all of the links in the arm. Remember, we passed self to the function because we're inside of the class arm, so we have access to all of these links, and we're going to loop over them. Each time we're going to access what was the last element in the poses list that we're building up. So currently, like on the first iteration, it's going to be 0, 0, 0 because that's what was there, and then we extract that out into x, y, and theta. So you can get that from the most recent pose. We then have x, y, and theta within this little loop here, and this is where the implementation happens. You want to replace these 3 lines to compute the new theta, new x, and new y, given the previous pose and the current link. So we have x, y, and theta. You'll remember like there was a phi term and there was a d term for this link's angle offset and length. And you can access those here with link.length and link.angle. So those are there, kind of filling out the pieces we need. And then the code just puts these into a new NumPy array, and we throw that onto the end of the list, and it'll continue on. So really you just need to do these 3 lines and everything else is taken care of. And once you implement that, the workshop should work. I'm not going to spoil too much because like that's the exercise. I suggest you go through it and do that. There is a answer.txt to copy paste if you do get stuck. But just kind of revisiting the algorithm, here's the pseudocode for it. We had some series of links, each with a length and an angle, and we want to output the location of the end effector as x, y, theta. So the way to do that is starting at 0, 0, 0, you're going to loop over all of the links, which each have some length and angle, and you can compute the new angle, as we've said, by adding these up. The x and y are, these terms, as we've said, and you loop over, then it ends, and you return the final result. That's the pseudocode. So between this slide and the code that's there, you hopefully can figure that out. Well, we have it anyway. So this is what we end up with. I've implemented things which, let's not show you, up there in the answer file already. So if you really want to just copy paste, go wild. But I think thinking through this is a useful exercise in Python. That's the entire point of the workshop. So I'm kind of moving around in the joint space right now, kind of sporadically. Let's maybe think it through. So let's start in the center. Let's try to get it to a reasonable location like here. So here we have a very low theta 1 and a very high theta 2. So as we move this down, it should move theta to a lower and lower angle. So we can see that the angle is decreasing on the second link there. Similarly, if we go to like here, we can slowly decrease theta 1 in this direction. So we can see the first angle is decreasing, as we go along that way. We can actually get to the same position in 2 different ways here because, 2 pi is 0 in polar, I guess. But this is what it should end up looking like once you've implemented it. As one final trick, I'll go in and add, oh no, the GUI won't work. Yeah. Basically, like this implementation, we could add in more links, but this interface only has 2 links in the joint space, and I'm not going to change that live. So yeah, that's what it should look like. Hopefully everyone is able to get through that if you're interested in doing so. And if you have any questions, you can always drop questions in the Discord. Don't forget to like, comment, and subscribe, and we'll see you next week. There it is.